It's my pleasure to introduce Rebecca Harrington, who's going to talk to us today about the title that you can see here. Tell us some of the work that she's been doing, bringing seismic constraints into crustal studies. And Rebecca, if it's okay with you, because you know that our normal procedure and sort of mode of operation is that people will stay muted unless they have a question during the talk. And if it's some point of clarification, if you don't mind, maybe they'll interrupt. Otherwise, we'll
Sure.
Otherwise, we'll wait for main discussions and questions at the end, which would be around 5:30 at our time. So, but yeah, please take over, and thank you very much for organizing this.
Okay, well, thank you very much for the invitation. And yeah, if you do have a question that comes up or need a point of clarification, please feel free to ask me, or I have my chat window open too, in case anybody feels shy and wants to write something in the chat. I'll try to keep my eye on it. But I first want to acknowledge all of the co-authors that I have here on this talk. I'm kind of putting together a compilation of work that my collaborators and my students and I have done looking at earthquake source parameters. And in particular, we tend to look mostly at the static stress drop that we can infer from seismograms and try to figure out what we can learn about the faulting environment and what the trend or lack thereof of static stress drop can tell us about faulting conditions and rock strength. So, oops, I'm going the wrong way here. Here we go. Okay, so I know a lot of people who are present today also work on this problem. We all consider sort of a fault on a planar surface, or maybe we don't, maybe we can even start arguing about that. But if you want to start with this kind of simple model of a two-dimensional fault embedded in an elastic half space to sort of have some orientation for the type of problem that we're looking at, we can look at this rupture surface, this schematic fault on the top, and we can ask a lot of questions about what's going on that surface when an earthquake happens. So you can consider it as kind of the largest dynamic crack propagation on Earth. And people look at this at different scales and then try to find out, for example, if you look at the bottom plot, we're looking at sort of the stress as a function of slip. This is also a schematic plot. And I appreciate that a lot of people who are working in the laboratory would probably even take issues with this solid black line here and say that this may not even be realistic, or the fact that it even ends at the final frictional sliding stress. But essentially what we're trying to do in my group is to take this model, at least of the static stress drop, when a rupture happens on a fault surface, and sort of disentangle all of the different imprints that both sort of the processes on the fault that are going on, the observational constraints, and try to infer what we can about this stress drop, this static stress drop that we measure. So the difference between the initial stress and the final stress after the earthquake has happened, and disentangle those effects and try to figure out what that's telling us about what's going on the fault and the strength of rocks. And so this is really the quantity that and I know that everybody is looking at different sort of aspects of this problem, as I said, but this is the quantity that we're going to concentrate on mostly today as part of the work that we've done in my group and with my collaborators, is this static stress drop value. So we can start with kind of talking about the different ways that we measure stress drop. Whether you're a geodesist or whether you look at larger earthquakes, you might take a different approach. So you have sort of that, but basically the principle is the same. If you take that fault embedded in a medium and you look at sort of the average slip and integrate that over the area of the fault, this is what we're talking about with the static stress drop value. And if you're lucky enough to have a large earthquake that's close to the surface, maybe you can infer what that value is or measure that value with geodetic constraints, or you can use more sort of ensemble models to put seismic and geodetic data together and try to constrain that value. But by and large, I tend to work on small earthquakes. So usually there's no surface deformation that we can measure and try to make inferences about or measurements or modeling constraints on the stress drop values. So what we do is look at both the P and the S wave arrivals in the time domain, and then maybe sometimes convert those to the spectral domain as well, and then apply our favorite spectral model and try to assess or to estimate what the size of the earthquake is by the long period spectral amplitude and the magnitude of the stress drop with the corner frequency within the models you can see shown with the dashed line here. So the type of information, the assumption, just to make clear what the assumptions are when you're using small earthquakes to try to make inferences about the stress drop, we take that phase information from the seismogram. Here I have sort of a time series of a small earthquake where I have a time window shown, and already there can be inherent problems and many ambiguities on determining stress drop values, some of which I'm going to talk about today for these small earthquakes, even in the time window selection that we choose to then go to the spectral domain and estimate an earthquake spectra and do the spectral fitting that you see with the solid dashed line. And of course, the size of that event is going to be inferred from the long period spectral amplitude. And then the sort of the inverse of the duration of that event is going to be estimated with the spectral corner frequency. And by and large, from theoretical considerations, we can sort of get to this relationship where we see that we expect that for smaller earthquakes, the moment should scale as the cube of the duration, or you can alternatively say as the inverse cube of the corner frequency for tectonic earthquakes. But actually measuring that in practice, particularly for smaller earthquakes, and accounting for all of the sort of subtle effects that are imparted to the spectra when the waveform or when the energy travels from the surface of the fault to the station is not so straightforward and not trivial. So effectively, we take that information that we measure directly from the seismogram, this moment and this spectral corner frequency. And then you can invoke whatever your favorite spectral model is, and you can then get a relationship from these parameters between the moment and the corner frequency for the static stress drop. Now as I said, that sort of modeling assumption comes in here with this value of K that you assume. And then of course we have the the shear wave velocity here, which we assume to be constant. There's no good reason to assume that it should change with moment. So by and large, with this sort of expected relationship comes out that stress drop should be constant if the moment and the cube of the inverse cube of the corner frequency are indeed proportional to one another. Oops, sorry, my mouse is not responding here. There we go. Okay, so if we empirically look at some data, we can say by and large that we think that stress drop is relatively scale invariant, that this relationship holds. There are different studies which say that it may vary according to depth, it may vary according to faulting style, to magnitude, to tectonic setting. But probably what everybody notices about this plot where I'm looking here, if you want to use seismic moment or you want to look at magnitude, which is given on the scale bar on the top, and I have static stress drop here on the right-hand side, that there's a lot of scatter within these data, and it's varying. So you can call it constant, but it's sort of constant over 2 orders of magnitude. And so when I say that stress drop is relatively scale invariant, I am adding the qualifier here that this is, I do acknowledge that this is not necessarily an uncontroversial claim, particularly when we start looking at smaller earthquakes. So this is from a paper by Ida and Baroza from 2001, where they were looking at a compilation of data sets and sort of doing a spectral correction to account for energy which may not have or may have been lost or not observed or not accounted for because of observational constraints in the bandwidth or of the frequency of the observation. And when they correct that, they do sort of see that there is a more or less constant trend or lack thereof, a constant value for stress drop across a broad range of magnitudes for earthquakes, and that potentially there is not this perceived scaling of stress drop and magnitude as we get down to smaller magnitudes. Now, this is from a compilation, this is from a review paper by Rachel Abercrombie, which came out in 2001. And what you're looking at in the plot on the left is the, here she's plotting it source radius as a function of seismic moment. This is also a compilation of data going down to sort of magnitude -5 earthquakes. And we see that by and large, this relationship still holds 20 years later, that we've got more or less constant stress drop, albeit within 2 to 3 orders of magnitude, which seem to concentrate a little bit more when we get to larger magnitudes. And that's probably, or at least we think, a relationship that's probably true. But the question is, how much of this variation between 2 to 3 orders of magnitude is resulting from realistic differences between faulting environment, and how much of it is just observational constraints? Because as I said, measuring the stress drop from smaller earthquakes and estimating that spectral corner frequency in practice is not something that's completely straightforward to do. Now, you can, of course, relate the stress drop to the seismic energy, which is what they have shown here in the plot on the right-hand side. And this is just sometimes referred to in the literature as the apparent stress, which is just sort of another word that people use is the scaled energy. But why it's kind of important to know if this scaling is, or if there is a lack of scaling, if this tends to be a constant range where if we have lots of small earthquakes that we can observe, can we sort of extrapolate to larger magnitudes? I can give you an example in induced seismicity, because I work a lot with induced seismicity as well, is that when you're trying to infer behavior about large earthquakes, especially in areas of low historical seismicity rates, it would be very important to know sort of what these scaling relationships are and if they hold and under what conditions that they hold. So some of the, so in the work that I'm going to show you today that we've done, they're kind of addressing 3 main questions, which are centered around the theme of trying to understand what differences in stress drop, in spite of all of that scatter, might still be able to tell us about the faulting conditions. So I'm going to first, before we do that, kind of try to address how observational constraints affect stress drop estimates, because surely some of this scatter between these 2 and 3 orders of magnitude difference of stress drop values that we observe may be related to our limitations on our observations, particularly for smaller earthquakes. And in that effort to try to understand how stress drop is affected by both our observations and also the geological conditions in which the earthquakes can occur, we've done a lot of work looking at induced earthquakes because they do provide kind of a natural scaled up laboratory experiment where we at least have a little bit more constraint on the input stress perturbations that generate earthquakes compared to a completely tectonic setting where we're looking at only natural seismicity. So we have done a lot of work using induced earthquakes to try to get at these questions. And so then finally, once we sort of at least try to put in perspective how these observational constraints can affect our observations, then we start to ask questions about how can variations in stress drop both in space and time give us some clues about the geological faulting conditions under which the earthquakes occur. Okay, so I'm going to first start with those observational constraints, because especially for people who work on small earthquakes, they can really sort of appreciate how much actual scatter this can cause within measurements, even between different studies. And so there are 2 reasons we have sort of limitations on or variation on our stress drop values that we estimate, some of which are from limitations from the source. And so I'm going to start with those. And I'm going to call into question sort of our idea of what we think good seismic station coverage is when we start trying to place constraints on what stress drop values are or other source properties of earthquakes are. So these are just some plots from a paper by Yoshi Kaneko and Peter Shearer from 2015, showing the variation that you get. This is just meant to illustrate, depending on whether you chose sort of a circular source model or an elliptical or elliptical source model, the variation that you get here on a focal sphere, which is shown with the various colors here, is strongly dependent on the azimuth at which you make a measurement. So if you imagine that a seismic station is taking energy from one ray which traveled off of one point off of the focal sphere, you might, depending on where your station is located, get an extremely different measurement or estimate of energy from if you were to take it from a different point. There are also observational limitations which are not related necessarily to the source, but the travel path. So here I have just, of course, for illustration purposes, a schematic diagram of a fault. And so I'm assuming probably all of us have seen a real fault in the field and know that that planar source model is not very realistic, and that faults are more like fault zones, and that we have all of this fault core and damage zone structure around faults. And so when we have an earthquake on a fault surface, those waves travel outward from the source region, are recorded at a station. We record the ground motion, but there's also the imprint of the travel path in the material through which the source travels, which can obscure our version of the spectrum that we observe. And so, of course, that this is just here schematically shown that we're kind of blurring our image of what we see due to the fact that we have this travel path through which our waves are transmitted, and that is effectively going to change what we measure and what we estimate in terms of spectral properties. To add to that too is then, of course, which I'm not really going into here, is we have all kinds of different instruments by which we make these measurements. They are sensitive or have a flat frequency response in different bands. And so our bandwidth of observation is also going to have a big imprint on what we measure. So the question is then, are there mechanisms or ways or methods to circumvent the signature of the travel path and to account for the fact that we have different sources? Yes, there are. Each of them has their own caveats that we have to be aware of when we're using them. The most common type of approach that we use is what was termed as a spectral ratio approach. And so individually, when we estimate an earthquake spectrum, we can take a single station and a single earthquake measurement and fit the spectrum like I showed you with that sort of dashed line that you saw, and try to estimate what we think the attenuation is, and then try to account for that in our estimate. And we can get lots of measurements that way. But in the spectral ratio approach, what we can try to do is then sort of take two co-located earthquakes. They have to be slightly different sizes, at least a half an order to an order of magnitude in difference. And then we can make use of the fact that they have the same sort of path-related effects and try to cancel them out. So I'll just go through this quickly just to summarize. I don't want to spend too much time here, but for those who are not familiar, if you have an event pair, you have a larger event which has some sort of source time function. This is going to be the signal which is coming from the slip on a fault surface itself. It's convolved with the travel path, with the instrument response, and then what you measure on an instrument is the seismogram. But ideally, what you want to do is get rid of, when you're trying to estimate a stress drop, is get rid of that other information and isolate the information which has only to do with the source time function. So you can use this, what we typically term as an empirical Green's function event, which we assume is much, much smaller, and in relation to the larger event maybe has a source time function which can be approximated as a delta function. But the travel path and the instrument response are the same. And so you end up with a seismogram that looks very similar, and you can sort of cancel those effects out And if you were to look at this in the spectral domain, essentially, you can find two co-located events by finding something with very similar waveforms and looking at what their spectra would look like. The larger event would have a higher spectral amplitude and a lower corner frequency compared to the empirical Green's function. And then if you have a ratio, you can fit this ratio using an analytical function. And again, your favorite source model, if you like Brun, Boatwright, Sato, and Hirasawa, for example. And then you can remove those non-source related effects from the spectra and estimate or provide a more accurate estimate of the corner frequency. And the advantage to using these types of estimates relative to a single spectrum estimate is that you avoid this underestimation of the corner frequencies of the events, which is commonly what happens when you use a single spectrum approach and try to just sort of take an educated guess of what the attenuation is. But the drawbacks of this approach is that you significantly reduce the number of events for which you can make estimates. And this is then compounded by the fact that you may have only a small frequency band available to you, in which sometimes only the corner frequency of the larger event is available. So then you only end up with one corner frequency estimate. And this is more commonly what happens. Okay, so that, yeah, the narrow bandwidth here can provide a reasonable fit, but if your bandwidth of observation is not wide enough, even removing those effects of attenuation can be problematic, and you may still come up with an estimate which is not reflecting the true moment or the corner frequency of the pair. Okay, so let's get into some of our actual data and see how we've kind of tried to figure out what the limitations of station coverage are in terms of making these stress drop estimates. So this is from work we did using the LASSO array, which was a nodal seismic deployment performed in Oklahoma in 2016. And we had about 1,860 nodes, which were deployed at about 400 meter spacing. And here's the footprint of the array, which you can see in the larger plot. And in the inset here, this is just on the border, the Kansas-Oklahoma border, where there were a lot of induced earthquakes going on from saltwater wastewater disposal. And so each of these little diamonds here are showing one of the nodes, and the little brown dots are showing the earthquakes which were recorded when the deployment took place. And then the little beach ball solutions are the fault plane solutions that we came up with for 11 earthquakes around magnitude 2 plus or minus during the time the array was deployed. And what's kind of interesting here is you can see, so for this earthquake, which is labeled 1, whoops, I lost my mouse here. Here we go. With the pink sort of fault plane solution, the different nodes here are color coded according to the polarity of their first motions for this earthquake. And so you can see the in fact, the up and down polarity fits very nice, as you'd expect with the beach ball solution. I should note these sensors were vertical component only, so we only worked with P waves in this study. But what we wanted to do is explore the sort of estimate stress drops for these events and explore how, by considering different sort of combinations of stations, do our stress drop estimates change if we were to not have 1,800 stations available to us, but let's say anywhere between the range of 5 or 50 stations available to us. So this is for a particular event. We looked at different sort of events and looked at our corner frequency estimates and our seismic moment estimates. And what we saw is that there is a definite trade-off if you take any individual node. So each of the individual nodes here are shown with a little spectral line in the little windows here of the subset. And there's definitely in the fitting a trade-off between the corner frequency and the seismic moment. Whereas initially we always thought that the seismic moment was a fairly easy parameter to constrain because we don't have a strong attenuation effects at the lower frequencies. But here, even in this example, we can see that there is a trade-off. So this is for single spectrum fitting, what I'm showing here on the top. But we also had some cases where we could do some spectral ratio fitting and make more precise corrections for the attenuation and get better estimates of the seismic corner frequency. So this is kind of a little bit of a complicated plot, but you can just imagine here that, so we had a case where we took, here we took the, a subset of, or actually in this case, we took all of the stations and performed spectral ratio estimates and then plotted the spectral ratios here. And what you see with this sort of colors ranging from the cool to the bright colors is the density of the overlapping spectral ratios from each of the stations. So where you see warm colors, this is where there's a lot of overlap for individual nodes. Where you see individual lines or cooler colors, there's not as much overlap. So in a sense, it's showing you kind of the distribution of the, in a visual sense, of the spectral ratios. And then we have the stacked spectral ratio, which is shown with the solid black line. And then the two corner frequency estimates, which are shown with the Boatwright spectral model, which both the Brune and the Boatwright were shown, but we used the Boatwright because it fit the data better, which is shown by the red dashed line, where the Boatwright is shown with the black dashed line. And these are the corner frequency estimates, which are shown here along the frequency space. So what was interesting is we did this for all of the single spectra that we could, and we did this for all of the spectral ratio cases that we could, to try to get a sense of how much variation there is when you take a subset of the 1800 nodes and assuming that sort of a random subset that already you have anywhere ranging from, so here are the sample size, the x-axis is showing you the number of stations. So we have 10 stations, a subset of 10 stations drawn randomly, stack those spectral ratios here in this case, or stack those single spectra, make a moment corner frequency estimate, and then calculate a stress drop value here for 20 stations, 30 stations, 40 stations, and 50 stations, and so on. So just to take as an example, oops. I thought I had arrows here on this plot, but if you just take an example of, let's say we take draw 10 random stations from our subset of our 1800 nodes. We see, and then also we have different lines here showing you the maximum azimuthal gap of those 10 stations that we took. So depending on, let's say best case scenario, we only have a maximum 45-degree azimuthal gap. If we take the single spectrum estimate, we only have 10 stations. We see that if we do this for a random sample of do this 500 times, that 95 of our, whoops, where's my mouse? Here we go. 95% of our samples will have at least a 40% deviation from the mean. Even with a sample size of 20 stations, which by all means for a standard seismic deployment would be a fairly large number of stations for this small spatial or region, we still have a variation of within 30% and so on. So you can see that we have quite a large variation within our estimated stress drop values. And here I'm just showing you the estimated stress drop values for these events that we had within this lasso array. The darker shaded areas are showing the single spectrum estimates, and the sort of salmon colored and golden color are showing our spectral ratio corner frequency estimates. And you can see that you would probably, if you were only using single spectra, infer that the stress drops do get smaller with smaller moment values and so on. And so there's quite a wide variation. In some sense, this was, I have to admit, a bit sobering with respect to the fact that even for 20 and 30 stations that we had still such a large variation in our precision. So increasing precision of spectral ratio, or even for spectral ratios, increasing the precision may require 20 stations or more, which, as I said, for a standard seismic deployment for a spatial area this large is quite a bit. And that's assuming that you have a 45-degree azimuthal gap. Of course, it gets worse if your azimuthal coverage is not good as well. Okay, so then we can ask the question, are there differences between natural and induced earthquakes? Because like I said, a lot of people are looking at induced earthquakes and finding oftentimes that induced earthquakes seem to have lower stress drop values. And so the question would be, why is that? You can imagine a number of conditions under which induced earthquakes are generated, why that might be the case. But what we want to get at are what are some of the implications for the faulting conditions. So this work is centered around a temporary deployment that Yajing Liu and I from McGill ran in Northeast British Columbia in the Montney shale play, where a lot of induced earthquakes were generated. Here, showing the inside of the map, here's the border between British Columbia and Alberta. And we have these stations, which are this sort of very dense deployment of about 25 broadband stations for the most part over most of the deployment period that we're looking at. And we measured in a 3-year period about 8,000 earthquakes, which are shown here with the color-coded dots according to time during the deployment. And so we first wanted to kind of look at if there were differences between these natural induced earthquakes. So we first asked the question, are these definitively induced earthquakes? And what I'm showing you here is a histogram of the earthquakes as a function of time. And what you can see with the kind of aqua colored plot is the daily cumulative injected volume per well, which we had reported from the BC Oil and Gas Commission. And the gray shaded areas are times during hydraulic fracturing treatments. And you can just visually sort of qualitatively see that a lot of the earthquakes are being generated when there was injection activity going on. And then we just have the cumulative seismic moment curve here, where you can see there was a large earthquake, a magnitude 4.5, which is generated right within the middle of our array during that period. And so I think probably with the histogram and the spatial correlation between the wellheads, it's not difficult, or I don't think it's very controversial to say that probably a lot of these earthquakes were indeed induced. And so then we ask the question, okay, well, are these then sort of normal shear failure events, or are they related to the hydraulic fracturing process itself? Why is this area so susceptible to induced seismicity? So we did some very careful relocations of the earthquakes, and we see that here I have the direction of the maximum horizontal stress being shown, and we see that we have a lot of events which are suggesting that they're occurring on vertical strike slip oriented faults, which are optimally oriented in the stress field. Again, they're very well spatially and temporally correlated with the injection activity, but they seem to be reactivated naturally pre-existing faults. And they don't necessarily seem to be related to sort of mode 1 crack opening resulting from the hydraulic fracturing activity. So then we started asking, okay, well, are these source properties of these earthquakes different? What's different about them? What's similar between sort of natural tectonic events? So for the larger events, we performed fault plane solution, did estimates of fault plane solutions. And we saw that we have generally 2 kinds of populations of events which are consistent with what are known about the mapped faults in the area. We have some Graben bounding normal faults, and we do see some indication for some normal faulting going on. And there is some suggestion that a lot of the, thrust faulting, I don't know why I said normal faulting, it was thrust faulting going on because these Graben bounding faults are reactivated in a thrust sense, or in a reverse sense, I should say, probably more accurately. And then we have a lot, and these tend to be, at least in some cases where we have good constraints on depth, these look like a lot of times they might be basement reactivated faults. And then we have a lot of faults which are happening in the more shallow sedimentary layers, and these are optimally oriented in a strike slip sense. And just as a quick check, we also sort of looked at the Gutenberg Richter distribution and find that these events tend to follow a sort of standard Gutenberg Richter distribution. Maybe there's a little bit of depletion here in the higher magnitude ranges, but again, this is only a 3-year period, and so I wouldn't read too much into it, but the B value seems to be around 1 for this distribution of the events. So for those events, we also very carefully estimated stress drops using spectral ratio approaches, and we found that these earthquakes do not have particularly low stress drop values. They're comparable to tectonic earthquakes within the area. So what you're seeing here are the stress drop values from P waves and from S waves, where the diamond is scaled by the number of EGFs that we have available for a particular event pair. And they fall within the 1 to 10 megapascal range. So although these are intraplate events, they fall on the sort of lower end of the range that we typically see within the Western Canada Sedimentary Basin. We've seen some higher values a little bit further east in Alberta, but they tend to behave like completely, I should say, garden variety normal earthquakes, which were generated by tectonic loading. So we've also been looking at in a little bit more detail. Now this is up a little bit further north, located near Fort St. John. Again, you can see where we are in the insets a little bit further to the west, where we had an array of 8 seismometers installed around. So here we're looking at the regional map on the left, where you see all of the wells and the seismicity in a 2-year period. And then here looking at the right within the box, this is the location of where we installed this small array of 8 stations around an individual well before and after a hydraulic fracturing treatment took place, just to examine the seismicity and the characteristics of the source properties of the earthquakes that were associated with this hydraulic fracturing treatment. So we recorded all of the events that you see with colored dots here. Only I would say the locations which are closer to the array, of course, are very well constrained, but the ones which are plotted in blue temporally correlate with well treatments, which are shown by these different hydraulic fracturing wells. And in particular, we focus a lot of attention on this cluster 1 and cluster 2 around the well, because we did see some migratory behavior, which allowed us to kind of estimate the diffusivity of the rocks at a value of about 0.2 meters squared per second. So for this initial case, or this is from work that my postdoc did, she has 2 papers related to actually she has 3 papers related to this, but this is from work that she did in the earlier paper, where she just took sort of the single spectrum approach, and then also kind of a clustered event approach, and estimated the stress drop based on the single spectrum fits. And what she found is that there was a spatial correlation of the stress drop and as it relates to the distance to the hydraulic fracturing well. So I'm going to focus on this well here, this hydraulic fracturing well 1, where you can see the little, I forgot to explain, these little lines here are showing the horizontal trajectory of the well. But what you can see here in the plot on the left, here this is map view, and we're looking at depth on the 2 panels on the right. And you can see from the color bar here that the stress drop values for the events close to the well are systematically lower relative to the events which are further away from the well. Now, again, I already pointed out that there are some problems with single spectrum approaches, and that they typically underestimate the corner frequency. But you can generally trust the relative differences between stress drop estimates for a particular data set as long as the azimuthal coverage is similar and the approach is the same. So while we don't necessarily believe the absolute values that we have for these stress drops with the single spectrum approach, we do believe the relative differences, or have reason to suggest, or evidence to suggest, that they could be consistent. So as I said, around this cluster 1 and cluster 2 seismicity, which was located very close to the well, have systematically lower stress drop values relative to the other values. And what I didn't go into much detail here, but she, as I said, she used this single spectrum approach. She also used another similar approach where she clustered, or she took clusters of events which were very close to one another and estimated their seismic Q quality factor individually to try to get constraints on what the quality factor was with the spatial distribution, and found consistently that the seismic quality factor close to the wells was also suggested to be lower by her estimates and grouping these earthquakes into individual clusters, which would be consistent with what we understand from the process, that the rock damage and or the pore pressure should be greater as you're closer to the well, where you're creating this fracture network. That's the whole point of doing the hydraulic fracturing. And that's consistent with what we observe with, or what we estimate with, the seismic Q values. Now, what was particularly interesting about this data set is she really went through and created this catalog of about 350 earthquakes in this 5-month time span by hand. And she used automated methods initially to detect the events, but then went through and combed through everything by hand. And she found what we refer to as sort of typical induced earthquakes. They don't look any different than sort of standard tectonic earthquakes. And she also found a different type of event, which we refer to as EHW. This is giving you an example of, or two representative examples of these kinds of events, whereas the black waveforms are showing you these typical induced earthquakes and these EHW events. And if you just look at the panels with the waveforms here, qualitatively, you'll see that, well, they look a little bit different. The apparent duration of the pink traces seems to be long for a similar magnitude relative to the black traces, which could be a waveguide effect, it could be a path effect. But what the first line of evidence that sort of convinced us is that this is actually a difference in the types of sources between these two events, is that if you compare their initial P pulse, you'll see that the typical event has a narrower pulse, suggesting that it has, and that width of that pulse will be proportional to the duration of the event, and that these EHWs, and you can look at the S pulses too, you can see the same effect, that the pulse width is wider. And there are earthquakes which are these EHW and these typical events, which are in more or less the same location. So it's not that this is a dispersion effect and we see this widened pulse for events which are further away, but these two types, or different types of earthquakes, are also happening in the same location. And there are some of these EHWs, that's I forgot to tell you the acronym is earthquakes of hybrid waveforms, but we use this acronym, although it's a little bit awkward, because what you see, for those of you who have probably looked at volcanic earthquakes, you might say that they kind of resemble, the waveforms resemble hybrids. We didn't want to call them hybrids because we didn't want them to be confused with volcanic hybrids, because we don't think this is related to a volcanic process. So we gave them this EHW acronym. We see that some of them are happening close to the well, but then there's another group which happen very close to, or if we fit a, they seem to make sort of a planar structure. If we fit a fault planar structure, they all have a very close fit to within 100 meters of this planar structure. Yeah, so this was kind of an intriguing signal, and we wanted to kind of know more. So what we did is we took the initial part of the waveform, the P and the S wave arrival, and used spectral ratio approaches and estimated the moment and the corner frequency for these hybrid frequency waveforms, these EHWs, and for the sort of standard induced events. So the EHWs are shown with the aqua color here. The standard induced events are shown with the sort of gray colors here. And we just overlaid them on this standard plot that probably everybody's familiar with from a number of papers, but which shows the kind of moment scaling relationship for, or inferred moment scaling relationship for slow earthquakes, also, which may be controversial, I acknowledge, but also for fast earthquakes where we have moment being proportional to the duration cubed. And then up here, I just have some example spectra and spectral fits of these different types of earthquakes. But what you can probably see is that for these EHW events, we don't have a wide magnitude range, but we don't have any reason to believe that they don't fall along this moment duration cubed scaling. So as such, we decided to kind of look at their scaling, estimate their stress drop value, and use a crack model. And what we find when we estimate the stress drops is that the scaling seems to be similar, but that they have what might be what are lower stress drop values, which we would say imply that these events have a longer duration, which could mean that they have a slower rupture. So if you recall from this spectral plot, we have our source spectrum where the long period spectral amplitude is proportional to the size. Where the spectra starts to bend over is the corner frequency, inversely proportional to the duration. We can invoke our favorite source model, estimate a stress drop value. And when we have these EHW events have lower corner frequencies, and these lower corner frequencies imply two possible scenarios. Either one, that the rupture velocity is the same for the slow earthquakes, but the stress drop, so in this, the stress drop, I'm referring to the ratio of the slip over the length, that has to be low. Or in scenario two, that the stress drop is the same for the EHWs and the regular earthquakes, but that the rupture speed for the EHWs is lower than it is for the typical events. So we can take a look in detail. As I said, there are EHWs which are very close to the wellbore, and then there are these EHWs which are still relatively close to the wellbore, but sort of form this planar structure, or at least can be fit well by a planar structure. And we can look at the different sort of velocities, and here I have just the seismic moment versus the corner frequency. Here we have our standard earthquakes with the isolines of stress drop here, where the standard earthquakes are shown with the little gray dots, and this population of EHW events is shown. They have lower stress drop values. We have this inherent ambiguity with these smaller earthquakes. We have to make an assumption about what the rupture velocity is. And if we make an assumption of constant rupture velocity, then we come up with a lower stress drop value. But if we assume in scenario two that we have sort of a similar stress drop and that the rupture velocity might be lower, then we can see that we also can potentially have a range of rupture velocities for these EHWs. And so the interpretation could be that, and given that all of these are sort of close to the well, and also with the previous work that Hongyu did, where we have what seem to be very low Q measurements close to the well, that these all offer consistency arguments that scenario two is probably more likely. Although both scenario one and scenario two would be consistent with having sort of weak rocks close to the wellbore. But our interpretation with that is that if you consider scenario two, that our Q values are lower close to the wellbore, and you can imagine that we could have potentially lower rupture velocities for the EHWs, we hypothesize that these could sort of mark a transition between aseismic and seismic rupture. There's been some modeling work and more recently some observational work with geodetic means by some part of from Thomas Ayer and Dave Eaton and others, which have inferred that there is in fact aseismic slip associated with injection activity also in the Western Canada Sedimentary Basin. Modeling work that's been done as well to suggest that there is an aseismic slip going on close to the wellbore. And so if faults really do slip at a continuum of speeds, probably where you have a high density of stations and a good signal to noise ratio, and you're looking in detail, then you should probably also see evidence for some intermediate form of rupture between aseismic and seismic slip, or in other words, sort of slower slipping earthquakes. And so we interpret this as a possible indication that these types of EHW or hybrid looking earthquakes might represent that boundary between aseismic slipping and seismic slipping. So to go back to those questions that I posed at the beginning, sort of how do observational and at least try to provide possible answers for them, at least within the context of the work that we've done. For the first one, how the observational constraints can affect stress drop estimates. I think our study with the LASSO data, as I said, was pretty sobering, and that what we thought up to this point was good coverage may not actually be all that good, particularly when we're looking at smaller earthquakes. And hopefully, as more and more types of nodal seismic data become available, maybe we will be able to provide some insights into what kind of resolution we actually need. But then once we sort of take those caveats into mind and start trying to get at differences between natural induced earthquakes and what we can learn about rock strengths with those kinds of caveats in mind, it doesn't look like, for example, between natural induced earthquakes that there are any physical differences. There's more compelling evidence based on what we've seen for variation within rock strength and material properties, which for me provides more motivation to continue looking at induced earthquakes to try to learn about natural earthquakes and how lithology and faulting conditions make an imprint on the types of observables that we use to try to study them. And then finally, what variations in stress drop can tell us about faulting and geological conditions is once we keep those sort of caveats about what we're looking at in mind and what constraints we have on our data, when we keep that in mind, we can still make a lot of inferences about where faults are weak, where rupture velocities might be slower. And I think there's a lot of merit in continuing to try to look at smaller earthquakes in even higher resolution with more types of data. Now, if I had sort of could put together a wish list of what I'd like to have to sort of continue this kind of work, I think that one thing that would be very helpful, particularly because there is still a lot of scatter and stress drop estimates. I mentioned when we started, I was at the Ridgecrest Community Stress Drop Experiment, where we're all looking at the same set of 50 earthquakes using the same data, and we're still getting a huge range in stress drop estimates, which is, yeah, frustrating to say the least. And I think that one thing that would be super helpful to try to kind of tie those estimates of stress drop to geological observations and know more about which assumptions are correct and which ones are not, it would be great to have more field observations. I don't know, from perhaps, I'm not a field geologist, but just as a suggestion to field geologists, maybe other people have thoughts on this, but old exhumed fault zones, earthquakes in the rock record, and try to find observations of actual stress drop or ratios between fault slip and fault length, and also to try to tie those observations to maybe earthquake or fault roughness to radiated seismic energy over a range of observational skills. So that's probably a tall order, but that would be maybe my wish list to have to tie together with the seismic data. And I'd like to also learn more about source differences between slow and fast earthquakes. And again, that probably ties into the first point too of things that we'd like to have. And this probably would have potential implications also for induced earthquakes. As I said, I think we're learning a lot from them. There's no reason to believe that they're physically different than sort of the tectonic variety of earthquakes. And I think that there's probably a lot still to be learned about what are differences between slow and fast slip, and what are the factors which sort of change it. This is just a little something which this is really, really new, but so if you have detailed questions for me about the method, my grad student just gave this to me a couple of days ago, but it's just some further support that we've been doing with this data set in BC, which kind of support the fact that probably there are differences in rock strength, which are observable through seismic data. So this comes from this data set, just to remind you here again, where we looked at clusters of earth. So within this data set, there are lots of earthquakes which have very similar waveforms. So we made use of that fact to look at differential, what are called differential VP-VS ratios. This is based on a paper from Lin and Shearer from 2006, the method. And what we found, so my student has been looking at differences between VP and VS ratios within that data set, and then putting together these clustered groups of earthquakes. And you see from the dots here, there are positive and negative variations in VP and VS ratios. And this is just overlay or underlain by a plot of injected volume, which is shown with the sort of gray shaded areas where the darker colors indicate higher injected volumes. And we sort of, so here are the differential DTS and these differential travel times with the differential VP-VS ratio. So the top is just basically the data, the bottom is showing you the VP-VS ratio and how it changes in time, which is shown by the line here. And so the first thing we did is just say, okay, I would just sort of hypothesize that as a injection or a hydraulic fracturing treatment goes on, so we have the cumulative injected volume here, which is shown by the histogram, the daily injected volume. I would have assumed just a first order, more fluid, VS goes down, VP-VS goes up, but we sort of have this somewhat puzzling trend with the treatment. So you can see here's the injected volume, then all of a sudden the treatment stops and you get kind of this drop and then this recovery of the VPS values. So we tried to say, okay, there's this recovery, we don't really know how to explain that. So can we come up with sort of a rock physical model to try and explain that? So we followed this idea that if we imagine within our rock volume that we have sort of a randomly distributed cracks with various aspect ratios, and that our fluid volume content could range anywhere between 0 and 20%. And then we consider, so the different lines here are showing a random distribution of cracks embedded in our volume with aspect ratios shown by this alpha value. And this would be the range of bulk moduli and shear moduli values that we could have given this range of fluid volume content and this range of cracks with different aspect ratios. And so we kind of tried to play around with this physical model a little bit and could imagine sort of different, so here I have here the log of the aspect ratio versus the fluid volume fraction. And this would be the corresponding, so the color bar shows the corresponding VP-VS ratio. And so what I'm showing here on the bottom is the measured VP-VS ratio with this blue solid line. And then these different trajectories of what could happen according to how we might expect things to proceed within a hydraulic fracturing treatment. And so these different lines here are corresponding to these different models here. Whereas you can see sort of when we get to this dark brown color, this is corresponding here to this red curve. We're getting closer and closer to a physically consistent model with the VP-VS values that we observe. And again, this is just sort of a first order approximation to try to come up with a physical model that's consistent with our observations. But it would make sense for what we would expect within a hydraulic fracturing treatment where you're increasing the fluid volume fraction and maybe decreasing the aspect ratio, or initially not doing much to it, then decreasing it. And so we see that this model is consistent with evolving crack aspect ratios. So this is work that we want to try to explore a little bit more, but it's sort of maybe another avenue to explore how changes in rock strength might evolve with known input conditions of injection. And so it's just kind of an interesting other avenue to pursue besides just looking at necessarily stress drop alone, to try to infer rock strength and changes in rock strength with perturbations and stress. Okay, so yeah, that's all I have.
Wonderful. Please, everyone who's here, unmute and let's thank Rebecca together.